Hi everyone, welcome to today's seminar. And before we start today's seminar, I'm going to remind you about our next deadlines. Our next assignment 3, the deadline will be on November 25th. Which is next Thursday. And then the deadline of preliminary version is on December 8th, which is about 3 weeks later. And I haven't checked your assignment 2 and also your proposal yet, but I will try to finish it within this week. I will try my best to finish it this week, yes. But this is just a little reminder. And today we are going to talk about random variables, standardizing variables, and two most important theorem or laws that you will meet in this course. They are the law of large numbers and also central limit theorem. And then we are going to talk about hypothesis testing and confidence interval. So first, we are going to talk about random variables. So basically, random variables are the variables which are random. So it's a numerical summary of random outcomes. And basically, there are two types of random variable. So the first one is called discrete, and the second is called continuous. So one example of discrete random variables is the outcome of rolling dice. So it is obvious that the result of rolling a dice can only have 6 results, which are 1, 2, 3, 4, 5, 6. And one example of continuous random variables are humans' height. So in theory, basically, human beings can have any numbers of heights, and to describe how the probabilities are distributed over the values of the random variables, we have the probability distribution. So in probability distribution, we can also categorize it into two types, so which are the same as the type of random variables. So one is discrete and the other is continuous. So we call the discrete one is a probability mass function, and we call the continuous random variables probability density function. So for the probability mass function, the probability is for each value of the random variables. So when we use the example of rolling a dice again, so we can see that, for example, the probabilities for getting 1 when you're rolling a dice is 1/6, so which is quite clear. But for the probability density function and also for the continuous random variables, so probability means the random variables falls between 2 points. So actually, we can never know that. For example, if you take the human's height as an example again, so we cannot know that the probability of 170 centimeters, but we can only know that the probability between 170 centimeters to 180 centimeters. So these are the difference between discrete and continuous probability distribution. And for the cumulative distribution function, so which is the probability that the random variable is less or equal to a particular value. So if we take a dice as an example, so the cumulative distribution function can be, for example, we want to know that what is the probability of getting a value less or equal to 3 when I throw a dice. So we just add 1/6 3 times and we can get 1/2. So we know that the cumulative distribution function at 3 is equal to 1/2. So this is the meaning of cumulative distribution function. And among all the continuous probability distribution, so normal distribution is the one most widely used. And there are several characteristics that you can keep in mind. So the first one is it is bell-shaped. So which means that most of the values is concentrated around the means, but not on the tails or on the extreme value. And the third is it is symmetric around the mean. And the third characteristic is that 95% of the probability is between the average minus 1.96 times its standard deviation, and average plus 1.96 times standard deviation. So you can keep in mind this number 1.96, which we will meet later. So yeah, so this is the slides talking about the example of human heights as the example of the normal distribution. So we can say that actually a number of people taller or shorter than the average height is almost equal. And actually we can also know that a very small number of people are either extremely tall or extremely short. So humans' heights are also an example of a normal distribution. And among all the normal distributions, so there is also one special normal distribution, which we call standard normal distribution. So the standard normal distribution is a normal distribution with mean 0 and standard deviation as 1. And the probability for a normal distribution can be computed using statistical tables for a standard normal probability distribution. So what does this mean? Because actually we can roll back to the slides here. So as I say that, the 95% of the probability is between average minus 1.96 times standard deviation and average plus 1.96 times standard deviation, right? So in the standard normal distribution, we know that mean is 0 and standard deviation is 1. So which means that actually in the standard normal distribution, 95% of the probability is between minus 1.96 and plus 1.96. So by transform the other normal distribution to the standard normal distribution, actually it will make us calculate the probabilities much easier. So this is also related to our next topics, so which is standardizing variables. So why do we standardize? So the first is that to make interpretation results easier or more sensible. So for example, when we are discussing about whether the smaller class size will improve the performance of students, and we conducted, for example, this experiment across several countries, but of course, it is easy to think that, for example, to quantify the performance, the students' performance, so each country will actually use different exams or different criteria. So if you don't standardize the variables, actually it's quite difficult to quantify the effect of class size on the performance across, like the students' performance across different countries. So this is the first reason. And the second is in the hypothesis testing, which we will talk about later, it makes life a lot easier. So remember the example that I'm talking about the standard normal distribution. So you can see here the below. So for example, we want to know the probability of a normal variable x found in interval between a and c. So actually, we are going to calculate the probability between c and a, and we know that x is normal, is following normal distribution. But if we directly calculate it, it will actually become very complicated. But if we transform it into a standard normal distribution with average 0 and standard deviation 1, it actually make life a lot easier. And the way that we do it is that, so the way how we standardize a variable is that we first subtract the mean and then divide it by the standard deviation. By doing that, then we can make so we can standardize x and transform it into another normal variable with 0 mean and standard deviation of 1. By this, and actually we can calculate the probability as the same when we directly calculate the probability of x found in interval between a and c. So yeah, so I just actually talk about what this slide is going to say. So by this, then we can use the new normal variable. New variable is the same normal distribution to calculate the probabilities that we need. So the way that we standardize is to subtract the sample mean from x and divide it by the standard deviation. And because this is a linear transformation, so actually it will not change the distribution because you did not expand or shrink the shape of the probability function. You just shift it kind of. So now I'm going to give you an example of how to calculate the normal distribution function by using the table that you can see on slides, and also how to standardize it. So now we can turn to whiteboard. So now I have an x, so which has mean equal 10 and standard deviation equals 100, and which follows normal distribution. So I want to know what is the probability for the variable x is between minus 206 and between 164. So this is what I want to know. And how we calculate this? So now we need to use the standard, we need to use the standardization. So since we know that the mean of x is 10 and the standard deviation of x is 100, so we need to standardize it. So it will become minus okay, sorry. I wrote in the wrong number. So the question is minus 186. So when we do it, we minus the mean, subtract the mean, and divide it by the standard deviation. And after we standardize it, it will become Z. So which is the standardized variable, which will follow the standard normal distribution. And then 164 minus 10, and then divided by 100. So by doing this, we are actually calculate distribution between Z, the distribution of Z between minus 1.696 and the distribution between and 1.54. And now we need to take a look at the table. So now we turn to the table. So you can see that. So this table is the probability of from the minus infinity to the z to the number. So since we want to know that the probability between 1.96 and 1.54, so we can take a look at here. So the first one is we want to know the probability of minus 1.96. So it's here. So this number is the probability of minus infinity to minus 1.96. And then another one is 1.54. So it's here. So this is the probability from the minus infinity to 1.54. So we need to use this one minus this one. Then it will be the difference between these two values. So look at so this will actually becomes the probability of minus infinity, so which will becomes z. So if we draw a picture, then you will understand. And this one is so here is minus 1.96, and here is 1.54. So to calculate the probability between 1.96 and also 1.54, so we need to know, so from the table, we know this small triangle area and this big gray area. And the difference is we use this big one and then minus this small one, then we can get the answer. So if we go back to the slide, so 1.54 is 0.9382, and the 1.961 is 0.025. So the answer will be 0.9382 minus 0.025, which is equal 0.9357. So this is the example of how to use the standard normal distribution table to calculate the probability. So now let's turn back to the slide. So if you want to have more exercise, you can email me and I can talk more about how to calculate this. And now we are going to talk about the law of large numbers and also central limit theorem. So the problem with small sample sizes is that if we only have small samples, then it will give less precise estimates than large samples. Since when we have only small samples, actually it can be really a big fluctuation between the values, and which may not be the true values of the population. So for example, now we know that the human's heights are actually follows the normal distribution. But for example, if you only have 3 samples out of all the people population, then actually you cannot really know that the true distribution of human's height is actually normal distribution. Because for example, if you only have 3 sample size, then first you have a person with 170 centimeters, and the other one is, for example, 150 centimeters, and the last one is 180 centimeters. Actually, you cannot know that. You cannot know the real distribution of humans' heights, and as a result, you need to make stronger assumption, or you need to have more complicated adjustments to draw the conclusion. So as a result, so actually we prefer large samples when we want to draw conclusions about the population. However, the large sample size itself is not a guarantee of reliable reliable inference of the population. So if the large samples if the large samples wants to become reliable, so there are some requirements that it should be. So the first one is the sample has to be random. So what does it mean? So it should not intentionally or purposely. So it should be without any manipulations. So just as the rolling of dice. So which means that observations will be identically and independently distribution. So which means that, for example, if you want to know the human height, so I should randomly pick up a person rather than pick a person from, for example, my friend first. So if I choose one of my friend, so if I chose my sample of human heights from my friend and then my family and the others, then actually it's not random. So then even I got a large number, even I got a large sample size, it cannot be reliable as well. However, if the sample size is large and the observations are identically and independently distribution, then we can make assumptions about the sampling distributions of the variables. Because first, it will become more tightly centered around the average. So this is about average, so which is the law of large numbers means. So when I have more and more when I have more and more observations, and those observations are randomly, identically, and independently distributed, then the mean of those observations will become more and more closer to the true mean of the population. So this is about the mean. And the second is that, so the distribution of those observations will be well approximated by a normal distribution with the mean as the true mean, and the standard deviation is the standard deviation is the and the variance is the variance of the population divided by the number of observations. And the standardized average is approximated by a standard normal distribution. So this is about central limit theorem and also law of large numbers. So let me repeat it again. So if the observations, so if the size of observations is large enough and the observations are random, then first the mean of those observations will become more and more closer to the true mean of the population. And the second is the distribution of the observations will follow a normal distribution with mean as the true mean of the population, and the standard deviation is the standard deviation of the true the standard deviation of the population divided by the square root of the numbers of observations. So now we can turn to R as to show you how this works. So now we turn to R. And first, I would like to show you the law of large numbers. So as we know that if the sample size is big enough and all the observations are random, then the mean of those variables will become more and more like the mean of the population. So I use a special command called rnorm. So rnorm is a command which will generate random samples following the normal distribution. So if we have 5, so 5 is the 5 samples with true mean equals 160. And standard deviations equals 15. Maybe I can use 2, so it will easier to present. So you can see here. So by choosing rnorm, so we randomly generate 2 observations from a normal distribution with mean equals 160 and standard deviation equals 15. So now we generate 2 samples. So the first one is 186 and the other is 161. So it's quite obvious that actually the mean of these 2 numbers are not 160, quite obvious, because they are both of numbers are more than 160, so they are not 160. However, if we make the numbers larger and larger, the sample size larger and larger, it will more and more closer to the true mean, which is 160. So I can show you. So we can see this. So mean, so the first one is this one. So the first one is 182. And the other, we make it becomes 5. And then 10. And then 50. 100. 1000. And then 5000. And then the most extreme one, so 1 billion. So you can see that as the sample size becomes larger and larger, the mean of those observations will become more and more closer to the true mean, which is 160. So this is how we show the law of large numbers. And then now we are going to talk about, show you the central limit theorem. So I in 1. So first, I create a vector of zeros. So this is x bar is a vector with zeros. So which I'm going to save the estimate of the sample average that I will calculate with the next command. So let me explain this comments again. So first I create a vectors with many zeros. Then I draw. Then the second command is a loop. So I do it like 500 times. So you can see here, because this is for 1 to 500. So the thing that I do is that I randomly draw 30 samples from the normal distribution with mean 100 and standard deviation is 10. And I randomly draw 30 samples out and calculate the means. Then I do it 500 times. And after that, I plot the distribution of these like 500 calculations. So we can know that if the sample size is large enough, then the sampling distribution of these means will be approximated by a normal distribution. And with the mean is the mean of the population, which is 100. So if we do this, so you can see that, oh, I think I should, wait a second. Okay, so let me modify the comment a bit. So it should be comma, not colon. So if I do this, then you can see that. So so the distribution of the sample means is actually well approximated by the normal distribution. And if you want to see, if we have a larger sample size, then it will become more and more like the normal distributions. So now let's get back to the slide. So this is, yeah, so we just finished the law of large numbers and also central limit theorem. So I will first use the slides to talk about the confidence interval. Then we will use another data set from R to elaborate it again. So the confidence interval so we want to estimate a 95% of confidence interval for the sample mean of school using LNU data. So the way like how we calculate the confidence interval is that. So first we need to calculate the mean, and then we need to calculate the standard error for the sample mean of school. So which is the standard error of school divided by the square root of the sample size. And then we calculate the lower and upper limits of 90%, 95% of interval. So which is minus 1.96 of standard error. And then we check the values. So basically this is what confidence interval is about. So what does this mean? So which means that, so if we draw some random samples from the school, if we draw like 100 times, and if we draw 100 times of the sample mean of school, and out of so 95 times out of 100 times, the values of sample mean will be around this range. So this is what the confidence intervals mean. So for example, if we want to know about the 99% of interval, so which means that 99 times out of 100 times when I calculate the mean of school, so those values, if I calculate it 100 times, and 99 times of the value that I get will be within this range. So this is what the confidence intervals mean. And for the hypothesis test, so it's actually similar. So I think I will still use R. I think it is still more clear. Okay. So let's go back to R. So, so I think I can finish it first in the slides without entering the R. So let's continue. So just like I said, so confidence interval means that, so here a 95% confidence interval means that if you take 100 samples out to calculate those sample means, which means that there are 100 sample means, right? And a 95 confidence interval means that 95 out of those 100 calculated sample means will locate within this interval. So this is the meaning of confidence interval. And it is also related to the hypothesis test. So for example, now we are going to test whether the average level of schooling in Sweden is equal to 12 or not. So which means that our null hypothesis is that the mean of school equals 12. And the alternative hypothesis is that the mean of school is not equals to 12. So since we don't know the population mean of schooling, so we use 12. So since we don't know whether the population mean of school is 12 or not, or actually we don't even know the population mean. So that's why we are going to use the samples to test it. So we use our sample average to represent our thinking about the population means. So now it turns to we are going to test whether the sample means is equal to 12 or not. So to do that, we calculate the mean of school here, and then we calculate the test statistics. So the test statistics is the average of school minus 12. So 12 is the so 12 is the hypothetical value. And then we calculate the standard error of schooling. And after we calculate this, and then we compare the absolute value of this t statistics with the critical value and decided to reject null hypothesis or not, or to compute the p-value. So what does this related to the confidence interval and the thing that we just said? So you can see that actually the way of calculating the t-statistics is the same when we standardizing the variables. So you can see here, so the mean of school minus 12 divided by the standard deviation of school. So actually it is standardized the thing that you calculate, because now we are thinking about 12 here as the mean of the actual value. So now it means that we are trying to find the probability of the mean that we actually calculate, the probability of we having this value when the 12 is true. Let me say again. So we can see that actually the way of calculating the t-statistics is the same when we standardizing the normal distribution, right? So we can turn back here. So when we standardize the normal distribution, we subtract the sample mean and then we divide it by standard deviation. And t-statistics is the same. So we minus 12 and then divide it by the standard error of school. So we also try to find what's the position of the value that we actually calculate. What's the probability of this value when the real mean is 12? So this is what the t-statistics mean. So for example, if now we calculate the absolute value of t-statistics is 1.96, then it means that when the mean is really 12, then the probability for us to have this value is 5%. So which is also the p-value. So I can draw a picture to show what I'm talking about. So, but actually this is also the, so actually we will delve into this topic further in the next seminar, but I think it is okay to talk about this first. So when we try to calculate the t-statistics, so just take 12 as an example. So now actually we first hypothesize that 12 is true. And then we try to find the position of the things that we calculated. So for example, I don't know, maybe 20. So this is the hypothetical value. And this 20 is the actual value that we get from R, for example. And now we are going to standardize it. So we transform this 12 into 0. And then for this 20, maybe it will become, for example, like 2.1. So we transform this by standardization. And this standardization is, for example, is 20 minus 12 divided by the standard error of school. And we know that this is also t-statistics. And so what is p-value? So p-value is this area. So p-value is how come? So p-value is the area outside the value of t-statistic that you calculated. So it's here. So this is, so here is the p-value. So basically, t-statistics is that if this 12 is true, then what is the probability for us to get the actual value? And this probability is the p-value, and the probability, the corresponding on the corresponding value on the x-axis corresponding to the p-value, which is a probability, is then the t-statistics. So for example, if now the hypothetical value 12 is true, however, the actual value that I get is 20, and the probability for me to get this value is actually 0.0001, so which is almost zero. It means that the mean should not be 12. Why? Because if the mean is really 12, then it shouldn't be that easy for me to get the value 20, because the probability of getting this 20 under this mean equals 12 is too low. So it means that it is unlikely for me to get this 20. So this is how this is how the t-statistics and so p-value works in this sense. So now when we go back to here, so we calculate the t-statistics by standardizing the value that we get. And then we after we get the t-statistics, then we compute the area under the curve to calculate the p-value. And how we calculate the p-value in R is by using this this command. So this is the probability of normal distribution. So which is also the thing that we would like to know. And then minus absolute value of the t-statistics. So this is how we do the hypothesis test of the population mean. And since in the assignment, you will meet the questions of doing the hypothesis test of two population means. So for example, test if the average level of schooling in Sweden is the same between men and women. And now it becomes that the null hypothesis is that the male schooling equals female schooling, and the alternative hypothesis is that the mean of men's schooling is not equal to the women's schooling. Then how are we going to calculate it? So to calculate it, so it's actually the same when we do this when we do the single case. So in this case, so t statistics is still the same. So t statistics, is still the same. So it's actually actual minus hypothetical divided by standard error divided by standard error. So when we do the two different means, so what we do is that statistics. So it is men minus women, because in the null hypothesis, so hypothetical mean is either one of it, so you can calculate. So actually you can make one as the means. And how we calculate the standard error in this case? So it is the square root of variance of men divided by the number of men plus the variance of women divided by the observations of women. So this is how we calculate the t statistics when we are comparing the means of two different populations. So this is how we do this. So if you still have any questions about the confidence interval hypothesis testing and also those theorems, don't hesitate to ask me, because I think this is the most difficult part, but also the most critical part for you to understanding the following course. So if you don't really understand what I'm really talking about, and actually I feel it is also difficult to explain it somehow. So if you feel difficult understanding what I'm saying, so do not hesitate to ask me about the questions. And so let me repeat all the things again. So first, the first thing is the central limit theorem and the law of large numbers. So when the sample size is bigger and bigger, and when the sample size is bigger and bigger, and those samples are random, then the mean of those sample means will more and more closer to the actual mean, and then the distribution of those sample mean will converge to the normal distribution with the mean as the true mean as well, but the standard deviation will become the the true standard deviation divided by the square root of numbers. And then we talk about how to standardize the thing. And then we talk about the confidence interval. So the confidence interval, for example, the 95% of confidence interval is that if I calculate 100 times of the sample means, and 95 out of 100 of those means will locate within the range of the thing that I calculate. And the 95% interval is the mean plus mean plus or minus 1.96 times the standard error. And this 1.96 is related to a normal distribution that we just explained. So within positive and negative 1.96, 95% of the value will locate within this range. So that's why the 95% of confidence interval is using the value 1.96. And then we talk about the hypothetical. Then we talk about the hypothesis testing and talk about how to calculate t-statistics. So which is the actual value minus the hypothetical value. So which is the value that you are going to test, and then divided by the standard error of the sample that you calculate. So this is also a kind of standardization to make the thing become the standard normal distribution and take a look at the probability of those things. So actually they are all related, but it is kind of difficult to notice that actually they are just like two sides of a coin and disconnected. So this is the seminar today. And if you still have any problems, do not hesitate to ask me. And thank you for listening.